Friends, today we have a seminar by Patricio Salgado-Rebolledo about fractional quantum Hall, and our scientific host today is Zung, who will introduce our speaker. Zung, please.
So, hi everyone. So we are happy to have Patricio today give us a seminar on quantum Hall. So he is a graduate. He's a PhD from University of Bristol in Belgium in 2015. After that, he held several postdoc positions at Chile, Belgium, Poland, and Austria. And from early this year, he will be he is a young scientist fellow at IPCTP, our naval initiative, and he worked mostly on non-relativistic gravity, and he now trying to apply his expertise to condensed matter system. And the first system is a fractional quantum Hall. And today he will give a talk about this topic. And let's welcome our speaker.
I would like to thank the Institute and also Zoom for the invitation and the possibility to present my research. So in this opportunity, I'm going to be talking about p-atic order parameters in the fractional quantum Hall effect from non-relativistic higher spin fields. And this talk is based on my collaboration with Eric Berchow from the Confulian and Domenico Palumbo, which was published at the end of last year. So as the title says, this talk is the main subject is the fractional quantum Hall effect, which is one of the most important problems in condensed matter physics. It's a topological phase of matter that hosts collective excitations with fractionalized charge and statistics. And the low energy physics can be captured by effective topological and geometric description. So effective field theories, lately there's been a lot of attention in the construction of effective field theories based on non-relativistic geometry and non-relativistic field theory. So some tools known from gravity, and in particular non-relativistic gravity, are useful in this context. Apart from that, the fractional quantum Hall effect can host non-topological collective excitations, and also some of them can be used, can be studied using tools known from non-relativistic gravity and also higher spin theory. So this is the outline of the talk. First, I'm going to briefly review the topological action, effective action for the fractional quantum Hall effect. Then I'm going to talk about the nematic and the tetratic order in the fractional quantum Hall effect, and also the Landau-Legendre effective field theory. And then I'm going to show how this Landau-Legendre description can be obtained from the Fils-Pauli equation in the spin 2 case. And later I'm going to generalize that to the case of tetratic order and higher spin fields. So the fractional quantum Hall effect is the quantization of the conductance in a two-dimensional electron system in the presence of a strong electromagnetic field, a magnetic field in this case, and so in the presence of a current in a magnetic field that's perpendicular to the plane where this current is produced. An electric field is also created that's perpendicular both to the current and the magnetic field. So what was found here is that the conductance takes quantized values, where nu here is called the filling fraction, is the electron charge, and h bar is the Planck constant. And later it was found that nu could even take fractional values, which is called the fractional quantum Hall. The first case corresponds to the integer quantum Hall effect. The second one is the fractional one. So in the low energy regime, the physics of the fractional quantum Hall effect can be captured by Chern-Simons theory. So the whole law that relates the current and the electric field through the response function, in this case is this conductance, can be obtained as the field equations of Chern-Simons theory of this type. So it's easy to see that the whole law follows from varying this action with respect to the electromagnetic potential A nu.
Is this correct? Is this correct? Now, if I take the relation with respect to a mu,
Yes.
I have the current. And the current
One
now
step,
has the first term and from the second term. So
Mhm.
what is the J mu here?
Well, J mu here is a current that couples to A. So if you vary A, you will get derivatives of A on the side.
No, I mean the effective theory for fractional quantum Hall only
Mhm.
have the first term.
Yes.
There's no second term after you integrate out the degree of freedom. So you
Yeah,
see
this is
that-
what I'm gonna do here. So in this case, I'm gonna introduce. So this is what you mean, right?
right, but you
the
see
field
that if
small a.
you integrate out small a,
Yeah.
you end up with the first term of your action, not the
Yeah.
second term.
That's true.
I think second term is a mistake.
Well, but it depends how you see it. So it's true that you can dualize this current and then you can introduce this field like in that way, right? That's what you mean.
No, so you see that the actions later,
Mhm.
you have the chain segment of small a and the mixed chain segment term of big A and small a.
Yeah.
If you write down the effective theory only with the big A,
Mhm.
the last term is not there.
Yeah, in this case, yeah, but you could also add a current on top of that here.
No, so if you define the current as a variation of action with respect to the gauge field,
Yes.
then basically the first term only give you the meaning of the current up there.
Yes.
The second term doesn't contribute.
Well, all what I'm saying here is that this equation can be obtained from an action of this type.
No,
Which is true. If you vary this with respect to A, and you
because
write the equation,
no,
you
because
find this.
because mix A is a background, you should not use this equation of motion.
well, what I'm going to use in this talk is
the
this
equation of motion
action.
for small A is okay to use.
Mhm.
But the equation of motion for big A.
No, I'm not going to use this one. I'm going to use this. So this is just a motivation and why to use tensors.
And you're seeing that if with the small a there,
Mhm.
you integrate out the small a, you have the first part of your action, not the
Yeah, this is what I'm going to say
Right.
here precisely. So if the thing is that if you have a Chern-Simons theory of this type, this constant here should take integer values due to the quantization of the Chern-Simons level.
Yeah, sure.
Then you can, if you want to have a fractional value for nu, what you can do is this trick to introduce small a and integrate it out to find again a Chern-Simons action of this type, and now with fractional
And
nu.
you see that from your last equation doesn't have the last term.
Yeah, this is just a way to motivate why to use Chern-Simons theory. I'm not saying that this action here is the same as the one up here.
You get this later.
Okay. So is there any question about this? Any other question about this point? Okay, just to remark the main point. So it's possible to construct a Chern-Simons theory with a fractional filling factor, starting from an auxiliary field small a that couples to the electromagnetic potential and integrating out small a. So on cube space, it's possible to study a different response function that's called the Hall viscosity. So if one takes the same effective action that I showed you in the first slide, now introduces a spin connection associated to the field bind of the spatial geometry. So Gij here is the spatial metric, which can be written in terms of some spatial field bind, and the curvature can be written as the exterior derivative of the spin connection, which can be written in turn in terms of the field bind after solving the torsion-less constraint. So one can couple, in this case, the spin connection again to the emergent field A and play the same game as before, integrating out the field small a. And that leads to a slight generalization of the theory I showed you in the previous slide, where now the spin connection is present. So varying this action with respect, so this is the point, maybe it's related to the point we were discussing before. You could now introduce currents and vary with respect to this action here. And this will give you a set of equations that are a generalization of the one that I showed you before. So now for the charge density, there's no only contribution of the magnetic field, but also of the curvature scalar associated to this geometry. And when you integrate rho to construct the charge, you don't only have the magnetic flux, but also there is a contribution of the Euler characteristic of this curved surface. In the same way, for the spatial current, for the electric current, now there is a contribution coming from the geometry in terms of this field, curly E, which is called the gravitoelectric field. And now there is, of course, a new current associated to omega. If one also introduces a current for omega and by the action with respect to omega, there is a new equation that introduces a factor that goes along the drift velocity, which is called the Hall viscosity. So this is, roughly speaking, the effective field theory for the fractional quantum Hall effect in the case of a curved spatial surface. And it can be recovered, the same action can be recovered starting from a system of non-relativistic electrons and integrating out the fermionic fields.
Sorry, may I ask you a
Yes.
question? I'm not this expert on the fractional quantum, but here the theoretical framework you introduced. Any specific filling factor you have in mind with this theory?
Well,
Is it quite a general for any fractional value of the mu?
well, I would restrict to the Laplace state, so I would consider mu taking values of this form, even though there are more complicated fractions.
Roughly state.
Yes.
Since that's next slide. So field theory that you have here can be general. Can capture all of the topological property. Perhaps general fractional quantum of state. You just change the coefficient.
But I'm not sure if it describes all possible fractional quantum states.
So it not capture everything.
Yeah.
It captures a topological sector.
Yes. Okay.
So for example, phi half you can put in this one.
Okay. But so there are constructions of this type that include the fermionic field. So we have discussed this also.
No, so the topological sector after so the small a here is can come from the fermion, but after you integrate out all of the field you get up to this point. This thing only tell you about topical response, but not geometry.
Yes. So yeah, I'm gonna discuss the geometric part later. So yeah, maybe that's a good way of saying it. So this captures the topological sector. That's why I'm introducing it as the topological action, but there are also non-topological, let's say, geometric excitations which require a different type of description that I'm also comment later.
So this section was just phenomenological, and then these guys in this quite modern papers, they just derived it through some microscopic calculations, right?
Yeah, they started with an action for non-relativistic electrons and consider the path integral. So there you can integrate out the fermions. Of course, the fermions have to be coupled to these background fields. Then you integrate them out, and you find. But it's a bit more general. There is some extra contribution for the gravitational Chern-Simons action. There is a shift here in this coefficient that comes from something called the framing anomaly. But apart from that, the same action is recovered. Okay, so apart from the topological sector of the theory, there are also collective modes that can be described using only topology. So one example is the so-called Girvin-Macdonald-Platzman mode, or GMP mode, which is also called the Magen-Boroton, and it's been identified as a spin-2 excitation in the fractional quantum Hall effect, and it has experimental evidence. So lately, some people have related these spin-2 excitations with the fluctuations of an order parameter associated to a nematic phase. So the nematic phase in the fractional quantum Hall effect can be obtained, for example, by tilting the magnetic field, the system, which can deform the orbits of the electrons, which are moving in the cyclotron orbits. So this creates a phase transition that, this breaks the rotational symmetry of the system, SO2, and can be described using a nematic order parameter known from liquid crystal theory. So in this case, topological order and symmetry breaking coexist. So this is what I was saying before. The GMP mode can be identified with the gap nematic fluctuations of an isotropic phase. So as I will show you now, the order parameter that's useful to describe the nematic phase is a tensor, which is traceless and symmetric. And also because of the reason, this has been identified as the fluctuation of a metric, which in this case would correspond to an internal metric of the system, which was proposed by Haldane, which unimodular. Unimodularity here means that the determinant of this metric is fixed to 1, and in that case, a perturbation of such type of metric is also given by a tensor of this structure. So I will comment on this just now. So, because of the incompressibility of the fractional quantum Hall liquid, not all the deformations of these orbitals, as I showed before, when tilting the magnetic field, are allowed. Only the ones that preserve the area are allowed deformations. So this restricts the diffeomorphisms to a subclass of diffeomorphisms that are called area preserving. And at the quantum level, the area preserving diffeomorphisms have been shown to be isomorphic to W infinity algebra, which is something that appears often in the literature of higher spin theory. So this is, in a way, a hint that higher spin fields could appear as collective excitations in the fractional quantum Hall effect. And indeed, there's been some work in this direction, and also there is some numerical evidence that higher spin fields can also appear in the fractional quantum Hall effect. It's not only the spin 2, but higher values of the spin can be allowed. So when tilting the magnetic field in the system that breaks SO2, the SO2 symmetry, as I said, there is a recent paper by Haldane who conjectures that the inversion symmetry, which is like changing x to minus x, and let's say in the plane x to minus x and y to minus y, is a fundamental unbroken symmetry of the fractional quantum Hall effect. So this has led to some people to rule out deformations that don't preserve a C2 symmetry, and to allow deformations that preserve inversion. That are compatible with inversion symmetry, and these correspond to two-and-fold this corresponds to deformations that preserve two-and-fold symmetry. So in this case, these are some examples of them. So all these deformations preserve C2, are invariant under C2, and also, so that means that they preserve, they're invariant under inversion symmetry. So, okay, so the breaking of the spatial rotational symmetry involves an order parameter, as I said before. And so these phases are going to be associated to nematic. The first one, which is the one similar to the figure I showed you before here. But the next one, the one that is characterized by C4 symmetry, is associated with the tetratic order, and this one would correspond to excitic, and so on. So for each each one of these type of deformations, one can associate some order parameter, and this is what I'm gonna talk about in more detail now. So, how much time do I have left?
Until 5 p.m. at least.
Okay, that's more than enough.
You can talk more if you.
So the nematic order describes a liquid crystal phase where mesogens, which are the particles that compose this liquid crystal, tend to align along certain direction. So in the isotropic phase, one considers some liquid crystal formed by some objects that we call mesogens. They are totally disordered. This is the isotropic phase, and when they tend to align along some direction, this is what's called the nematic phase, or partial nematic order, in the sense that they don't have to be perfectly aligned, but they have some freedom to move along the axis that characterizes the phase. So the nematic phase in this sense is an approximate preferred direction, which of course breaks the rotational symmetry of the isotropic phase. So if I want to define another parameter for the isotropic nematic transition, if one assigns a vector to each one of these mesogens, which I call L, with I labeling the mesogens, so the elements in this liquid crystal, and A is the vector in it. So it runs from, if you just take the values 1 and 2. If one takes the average of this vector, that's not a good order parameter to describe the phase transition, because it's zero both in the isotropic and the nematic phase. So what works is the average of the tensor product of two of these vectors. If one averages that, then inserting some like suitable normalization and a shift to make it be zero, the isotropic phase, this is something that allows to differentiate the isotropic and the nematic phase. In the case the nematic order is along the y-axis, so this is the value of this object Q, and the isotropic case is zero. And Q here is called the strength of the nematic order, and is given by this average. So if one wants to describe now nematic order along some arbitrary direction, not necessarily the y-axis, one can generalize this construction, and the form of the order parameter is this one in terms of the director, which is a vector which can be parameterized in this form. And also some people, instead of using this type of tensor, prefers to go to complex notation. In that case, since this type of tensor has only two independent components, one can construct a complex field in terms of these two independent components. So the conclusion of this section is that in order to describe a nematic order and differentiate it from the isotropic phase, the right order parameter to use is a symmetric traceless rank 2 tensor. So in order to describe the system, one can postulate what is known as the Landau-Degen theory. So if we write the possible terms that are compatible with SO2 invariance, so this one can consider this type of terms, and the Hamiltonian associated to this Lagrangian for Q correspond to a gap mode with quadratic dispersion. So this is the type of Lagrangian that has been used to describe the nematic order, also in the case of the fractional quantum Hall effect. So if we are to describe the nematic,
sorry, can you go one slide back? So this Landau-Degen theory, it it is designed not to describe the some phase transition to nematic phase, or how is it possible to see some phase transition to nematic phase from this Landau-Desgen Lagrangian?
Yeah, so one has to perform an analysis similar to Girvin-Landau, right? In the case, for example, of ferromagnetism.
Right.
So
we should vary K3 parameter to go to ordered phase, or what's going on?
yeah, so in the isotropic phase, you can stay only with the first three terms, but you can consider Q as small enough to neglect the other ones. But if you want to describe the symmetry broken phase, then you need to consider some higher order terms and then see what's the minimum of this Hamiltonian. Then
At this level, you just change the sign K3.
exactly,
Yes,
it's very similar to the 5 to the 4th theory.
Okay, yes,
One is to
right.
evaluate, like, yeah, to see the signs, etc.
Sign of K3, and that's then my question is,
The generic vacuum, yeah.
if we are in nematic phase already, so we break some symmetry,
Well,
why we have only a gapped mode, not a gapless mode for this?
well, it's because I have a term like that. So this is like a mass term for the.
So
For the theory.
you have this ground state of this. We have the non-zero expectation value of the tensor,
Yeah, sure.
the same as non-zero expectation value of scalar field in the K in Woodland are the same thing here.
But it seems like we broke a rotational symmetry here,
Right.
which is continuous.
Yes.
Where is Goldstone?
So the Q we have expectation value.
Yes, right.
Q is complex. Then you have the real, I mean the absolute value and plus the phi. The phi will be Goldstone. But in this case, we do not go to the nematic phi yet. And basically, the order of parameters still doesn't get to that.
We are not in nematic phase yet. Okay.
Actually,
Okay, yeah, right. So this is above the transition, so it's gapped. Okay. Now it's maybe.
but mainly I'm gonna be interested in the first three terms here. So I'm always gonna be like close to the isotropic phase. I'm not gonna go. Actually, this term I'm not gonna obtain from the higher spin theory because for that I need some interacting higher spin theory. So what I'm gonna be focused on is, let's say, the quadratic part of the Landau-Desgen description. Okay, so it is possible to couple this Lagrangian to the topological action that I showed you in the first part of the talk by introducing what is called a nematic gauge potential. So it is possible to construct a gauge potential out of the nematic order parameter, which can be coupled to the Venn-Z Lagrangian that I introduced in the first part of the talk through a term of this type. So it's possible to couple this connection AN to the heterodynamic or emergent field in the fractional quantum Hall, in the topological action of the fractional quantum Hall effect through a term of this type. And this allows to describe together the nematic Lagrangians, the nematic order parameter, and the topological sector of the field. So this theory can be obtained also from something that's called the bimetric theory of the fractional quantum Hall effect. So Gromov and Son postulated a theory depending on two metrics that's able to describe fractional quantum Hall states. And they also were able to recover this type of description in the linearized case. So in the bimetric theory, one needs to introduce two geometries. One is called intrinsic, which is given in the first line in terms of field line and also a connection. And similarly, one can introduce an internal geometry in terms of a unimodular metric, which I call now calligraph G. One can also introduce some field line for this metric. And the only difference with the first one is that we're going to constrain the determinant of this one to be 1. So it is possible then to construct a metric and inverse metric and a connection as well. And the additional structure, that's something very particular of this theory, that at least I never saw before, is a tensor constructed out of the difference of the Christoffel symbols associated to the two different geometries.
This thing appear very long for in the usually biometric theory of gravity when they do like relativistic, but biometric to have massive gravity. This thing appear there already.
This thing appeared. And so what's the name of this theory? Is
There's a woman named Graham, the same as the Graham cohomology.
Yeah.
But there's
the RAM, right?
You can find the paper.
But is it written in this way? Because I've been looking for this structure in some relativistic theory to kind of reobtain that, and I haven't been able to find it. But okay. Okay, so the theory that Girvin-Macdonald postulated is then constructed by taking the square of this object, the difference of the Christoffel symbols, and also a potential that involves both geometries.
So there may probably some hand-wavy explanation why you have two geometries, extrinsic and intrinsic. What is the meaning of this thing?
Yeah, so the idea is that the extrinsic geometry is clear because you have some sample and this sample could be curved.
Yes, right.
This is like what I was discussing in the beginning, introducing the spin connection and coupling to the Chern-Simons field in the first level. Now, if we're going to interpret the GMP mode or this nematic order parameter as a spin 2 field, so it's the fluctuation of some metric 2. So the idea will be that when you go outside the linearized level, this spin 2 field would be related to some sort of gravitational theory. But this is not the ambient metric, it's some internal metric.
Oh, I see.
Okay. So if you want now to construct like a fully nonlinear theory, this could be interpreted since you have your extrinsic metric plus now some new internal metric whose fluctuation is the nematic order parameter, then this should or could be related to a biometric theory.
Yeah, sorry.
Yes.
In the additional structure, are the indices, I mean, it look like you are subtracting one thing from the other and they're same.
You mean in this expression?
Yeah.
There is a head.
Yeah. So exactly. So the hatted objects are the intrinsic ones. So this is the intrinsic metric, and this one is the extrinsic one.
So
the same for the connection.
So you are taking intrinsic from extrinsic and then.
Yeah, and they couple through this type of term. So the action for the biometric theory is actually the square of DC, which is here, plus the potential that allows you to describe some symmetry rate. So in that sense, the nematic order parameter that before I called QAB, now because of notation it's QIJ, it's going to be interpreted now as the fluctuation of the internal metric. Since the internal metric has a determinant equal to 1, Q has to be traceless. And this is what we will identify as the nematic order parameter. Indeed, when linearizing this theory, which is coupled to the topological sector, now with two types of NC terms, one for the intrinsic spin connection, one for the extrinsic, this leads to the Landau-de Gennes-Lagrangian, which with the particular coefficients. So if one wants to reconcile the idea of introducing a nematic gauge connection that couples to the topological sector with the biometric theory, one has to in some way identify this intrinsic spin connection with the nematic order parameter, and that's it's indeed possible. So in the formulation I showed you in the beginning, we introduced a nematic gauge potential constructed in terms of the nematic order parameter, which coupled to the emergent Chern-Simons field from the topological action. And now in the biometric theory, there is a similar extra term of this form, which couples the intrinsic spin connection. The spin connection is associated to the intrinsic geometry with the same emergent field of topological action with some coupling coefficient. And indeed, if one solves the spin connection in terms of the field by using the condition of zero torsion for both the spin connection, the external one and the internal one, and on top of that one linearizes the field by defining some perturbation of the flat field length. This gives exactly the same expression for the spin connection that was before called nematic gauge potential up to a constant. So the constant C appearing in the nematic gauge potential introduced by Pacheco and collaborators, this one, is related to the coupling constant of the internal, let's say, the C term with this expression. So in this sense, one can interpret the nematic order parameter as a fluctuation of a unimodular metric. So the idea is now to generalize that to other types of orders. And the next one in the list of cases I showed you at the beginning was the tetratic orders. Now we want to consider some liquid crystal where the mesogens have C4 symmetry, not C2. So in that case,
sorry, you ended with a nematic phase. Probably, can you name some physical consequence which can be observed from this nematic order or something? Because it seems you are going to discuss the tetratic now.
This was in a way a summary of what was done before.
Yeah, but I'm not familiar with it.
Yeah, so what's the question?
Is there some, I don't know, the most interesting consequence of emergence of such order, I don't know. Because you constructed this nice theory, and what is the main yield, I don't know, for experiment for?
Well, some of the references I quoted before, that they have used this idea of the nematic order parameter, and they have contrasted this with the numerical simulation.
You also have the transport now, not rotational invariant. So the quantum Hall, if you apply electric field in X direction, or in Y direction, or the other direction, then basically the higher order term will not rotational invariant.
Right.
The transport is not rotational invariant anymore.
And so you have a different rational numbers for conductivity?
No, the leading term just fine.
Okay.
But you can have more.
Some corrections.
Correction, but depend on
what do these corrections affect?
If
it's not the number itself,
so the higher term, if you apply the non-uniform electric field, usually you apply in X and Y direction the current, the amplitude of the response current should be the same. But now it depends on the direction that you apply electric field.
And this can be measured experimentally with the accuracy.
Right. So the quantum Hall experiment, when they apply the magnetic field, they can see the transition, and they can see that the current is not rotational.
So they can see this nematic.
They cannot see exactly what happened here, but they see that
Consequences.
the consequence.
Okay. So what I want to do now is to generalize these ideas to the tetratic case. In the case, the messenger exhibit the C4 symmetry. This one. So it is also possible to construct in the same way as I showed before some order parameter that allows to differentiate the tetratic phase and the isotropic one. But in this case, if one again defines some arbitrary director, the order parameter turns out to be a rank 4 symmetric traceless tensor, which can be expressed in terms of the director in this way. So one can check from this expression that the trace of any pair of indices here is 0, and that is fully symmetric. And again, one can define Landau-Lejeune Lagrangian now for this, the more general order parameter following along the same lines as before. So in this case, we're breaking SO2 to C4. So it's a deformation that preserves C4 symmetry. And it's possible, like, I'm not going to show the details, but to define a gauge potential in the same way as done in the spin 2 case that can be coupled to this emergent field in the fractional quantum Hall effect. And then the Hamiltonian of this quadratic, now Lagrangian, has a similar form as in the spin 2 case, so it's also a massive field. So and this can be generalized to even higher orders. So for all the possible types of deformations that I showed you before, and even for the ones that don't preserve in two-fold symmetry, also for C3 or C5, it's also possible always to construct p-atic order parameter, like following this idea, the Lagrangian and the connection that can be coupled to the topological sector. And these order parameters can be then associated to some gapped excitation. So what I want to show now is how to recover this from a relativistic higher spin theory. I don't know if there are more questions.
Question about this. So nematic, I understand you have inclined magnetic fields and you have some symmetry breaking. How would you act here to induce this type of phase?
Yeah, the thing is that the tilting of the magnetic field is done through a quenching, so it's like an abrupt change that produces many types of deformation. It's not like a smooth change in the magnetic field. So it's like a perturbation that creates all type of distortions. Then you can have also this type of deformation.
So I think the same thing when you think about Chap multipole. You can have some monopole with vanish. You can have dipole, have quadrupole, and so on.
Okay.
Similar thing.
Yeah, the more dominant, of course, is the nematic, but then you can consider like more complicated cases that are less and less dominant.
So just to understand this, the picture that you were showing, that's the picture of the Fermi surface?
No, this is like imaginary, let's say, the formation of the orbitals, let's say. So in the case, for example, like this picture I showed here. So in the fractional quantum Hall, the electrons follow like cyclotron orbits. But if you quench the system, then these orbits deform. But because of the incompressibility of the fluid, these deformations have to preserve the area, and then you can see which ones like expand and like independent ones.
And are there some estimations how you can be close to tetratic transition or to nematic transition, which will emerge first if you start inclining your field? Because usually some order parameters are mostly more likely to emerge and some others are not really. So
Yeah,
your claim is that this order, tetratic order, can emerge before nematic in some sense.
No, I would say after. So in this paper I cited where they study the quench, they get at least spin 4. So the spin 2 that was like expected, they also get spin 4.
So on top of that,
it's harder to observe. Yeah. So then if you go even further, each time it's harder to get it.
I see. Okay.
So the contribution is, so if you compute like correlators, like the correlation function of the electron like density, the density current, so the electron density, so this expands in a series as a series in the momentum, and the contribution of these fields is time like higher powers of momentum. So when the momentum is small, they are smaller and smaller. Okay.
Sorry, when you said you had a quench, right, experiment in mind, what kind of quench did you have in mind? Like suddenly changing the magnetic field, or?
Yeah. Now,
I see.
what's the mechanism? Exact mechanism they use to do that? Yeah, I'm not sure. Yeah.
See. And in general, also these fields that you are talking about, these order parameters, they are not directly coupled to the electric electromagnetic vector potentials. Right?
Well, these ones are neutral excitation.
Right.
Yeah.
So
Yeah.
you will not probably be able to see it from those transport measurements. I mean, I'm trying to understand what Zoom said earlier, that you see these things from transport measurements, but if these are neutral, then how are you seeing these from transport measurements?
When you integrate out the degree freedom that couple with it and also couple with excitation.
It may
So you're
electric
saying that you small a t here, couple with small a, and small a couple with big A.
Okay.
Then basically, you can generate the IT couple with big A after you integrate out small a.
I see. So eventually they will couple with the electric.
So it's not direct, but
Okay, so before I run out of time, let me show you how this type of Lagrangians can be obtained now from a relativistic theory. So in the spin 2 case, the most natural Lagrangian for a spin 2 field is the Fritz-Pauli Lagrangian for Fritz-Pauli action, which is this expression. H mu nu is the spin 2 field, and m is the mass. C here is the speed of light. So the field equations associated to this action are the wave equation for the spin 2 field plus these two subsidiary conditions that impose the trace of H to be 0 and the divergence free of H. So a good parameterization for a traceless field is in the spin 2 case is this one. So here I'm separating. So if I split the indices of the relativistic field in space and time, so the TT component is a scalar. Then the Ti, let's say, or Ta is a vector. And for the tensorial part, this parameterization is what ensures that the trace of the whole object is 0. So S here is a symmetric traceless tensor that is purely spatial. So A and B are spatial indices, mu and nu are space-time indices. So because it's symmetric and traceless, S has only two independent components, so I can construct a complex field out of its independent parts. And the same for the vector field that I have here. So now one can introduce new variables in the problem if I want to consider a non-relativistic limit. So I introduce a new field Q and U related to S and B through this phase transformation, which depends on the speed of light. And also introduce here two parameters. So this one is the same mass of the field that I introduced before, and this here is some arbitrary constant. So then I can reconstruct some symmetric traceless rank 2 tensor QAB out of the independent components of the new complex field. And the same for the vector. So this is what's called UA, is the vector constructed out of U1 and U2, and QAB is the tensor constructed out of these two components here. So one can show that when the speed of light is large, the scalar and the vector are not independent of Q. So in the end, the rank 2 tensor is the only independent component.
So what is theta here? Cosine theta and sine theta. What is it?
Yeah, this is, I'm sorry, yeah, it's a bad notation, but theta is the angle that is here. So yeah, sorry for that, but the transformation should be e to the minus I theta q. So theta is this object. So I wanted to express in the end like this condition, the one that says that the divergence of H mu equals 0 explicitly gives this expression. And since I wanted to express it in tensorial forms, I have to expand these expansions here. But yeah, I forgot to add this definition. But theta is the phase. So when C goes to infinity, phi and U are not independent. And the only thing I'm left is the field equation for S, which after expressing S in terms of Q gives me this Schrödinger-like equation for QAC or QAD, which is the field equation associated precisely to the Landau-Degen Lagrangian. So in this sense, the Landau-Degen description for QAB, the nematic parameter, can be obtained as a suitable large speed of light limit of the Fritz-Pauli action. So in the spin 4 case, it's possible to do the same thing. Now this requires a bit more work. So again, one has to choose a parameterization for H, which is again traceless and divergence free. One has to introduce a rank 4 spatial tensor, which is symmetric and traceless again. But again, now a rank 3 tensor, rank 2, a vector, and also a scalar. But by defining these two components which are compatible with the tracelessness condition, this fixes all the other components. And again, associated with this rank 4 symmetric traceless field, one can introduce a complex field out of the only two independent components, and the same for the rank 3 tensor. For the rank 2 and the vector, I use the same as in the spin 2 case. So these are the only two new fields. So then again, for each complex field, I define this phase transformation, and out of the new field, I can reconstruct again a rank 4 tensor. When evaluating the the divergence free condition of H, this fixes all the fields in my parameterization in terms of the rank 4 field. And again, the field equation associated with the rank 4 field, it's equivalent to the one coming from the tetratic now, the Landau-Lagrange parameter. And now, since I showed the field equations, I want to finish like generalizing this idea to the case of the.
So can you go several slides back? How you came up with this theory for Pierce-Pauli equation for this tensor of higher? No, this is this is a gravity. Okay, yeah. And then you get a theory for 4 index objects.
Yes. Right, it's the same. So the Pierce-Pauli equation is actually the wave equation for a field of arbitrary spin.
So you can generalize it to this.
Yeah. So in their paper, Fritz and Pauli wrote this type of expression for a symmetric tensor of arbitrary rank.
Oh, okay.
The problem is when you want to go to the Lagrangian. So in the spin 2 case, it is possible to write a Lagrangian that leads to these equations right away. But in the spin 4 case, you cannot do it. You cannot find a Lagrangian only in terms of H that gives these equations. You need to introduce some auxiliary fields. So the last part of the talk is precisely that. So it's possible in the case of a spin S field to introduce a Lagrangian of this form, where now mu of k represents k indices completely symmetric. But you need to introduce for any given k, like a field with k-1 indices and so on. And this type of Lagrangian with the coefficients chosen in the very specific form lead to the Pierce-Pauli equations for a spin S field. And it's possible in this case also to parameterize these fields in a way that you recover the Landau-Lagrangian directly, not only the field equation as I showed you before. So this Lagrangian exhibits a gauge symmetry. So there are some transformations for these fields that's really complicated. And also the parameters in the transformations are not independent. They are subject to some constraints. But in taking all this into account, this is a well-defined theory for a spin S field. So K runs from 0 to S. And all the other fields with spin like S minus 1, S minus 2, and so on, these are arbitrary fields necessary just for consistency.
So basically the idea is that you can construct like, let's say with the 2 index, you can construct like 1 plus 1, then you have 2 and 0. 2 plus 2, you can have like 4, 3, 1, 0, and then the auxiliary field that constrain to the highest spin, right?
Yes, yeah. Okay. So, well, this is an example of the Proctor-Lagrangian. So this is the spin 1 massive case, which is, so this is kind of the way people constructed this Lagrangian. So one can restore the gauge symmetry that's lost when adding the mass term in the case of electromagnetism by introducing a Stuckelberg field. So now the massive, like the Proctor-Lagrangian can be made gauge invariant by introducing an auxiliary field such that the whole Lagrangian is invariant under this transformation. When you kill the gauge symmetry, let's say, but to fix phi, then you recover the Proctor-Lagrangian, which doesn't have any gauge symmetry. So in this case, it's possible to use the gauge symmetry to get rid of the auxiliary field and end up only with your original field. But in the higher spin case, it's not possible. So how could one construct this Lagrangian here? First, by taking all the possible terms in terms of A and phi, and then fixing these coefficients so that there is a gauge invariance. So this is, in a way, what's pictured here. You consider all possible terms that couple these fields, and then you have to fix the coefficients in a way that there is some gauge invariance with just a generalization of what I'm showing here. So in spin 2 case, this is the action in terms of a spin 2 field, spin 1 field, auxiliary field, and a spin 0 field. So this is the gauge symmetry. And again, one can eliminate the scalar by using the gauge symmetry to gauge fix it to 0 if you want. But you cannot eliminate the vector. Now, in the previous action, I showed you that depended only on H. That's possible because H there wasn't traceless. The point here is that I want to use a field that off-shell is traceless, so I can use the parametrization I showed you before. So if I introduce this parametrization for H, and also something similar for the vector and the scalar I just eliminated, I can again like complexify all the fields, define the new ones using the phased transformation. And what happens is that in the large speed of light limit, the spin 2, let's say, non-relativistic field decouples from all the others. And that's a way to recover the Lagrangian, the Lagrangian from a well-defined spin 2 theory for a traceless field. And the same thing can be done in the spin 4 case. Now you need to define also a bunch of auxiliary fields, spin 3, 2, 1, and so on. One has to parameterize these fields in terms of spatial tensors, as I did before. So you see for the spin 4 field, there is this rank 4 symmetric traceless tensor, which is the one I'm interested in. But there are also the lower spin fields that enter in this parameterization. And then I have a parameterization for the auxiliary spin 3, 2, 1, and so on. The point is that when complexifying all these fields, because all of them except the scalars have two independent components, introducing these phase factors and fixing the coefficients so there are no divergent terms, the highest spin field QS decouples from all the rest and is described as this Landau-Dijen Lagrangian. So this is a consistent way to obtain for any p-atic or the parameter to obtain the Lagrangian from a higher spin field. So the GMP model in fractional effect can be associated with another parameter describing an entropic nematic phase transition. So this is what was known. And also the Landau-Dijen Lagrangian captures the dynamics of these other parameters and can be obtained from an effective biometric theory at the linearized level. But this construction, the Landau-Dijen Lagrangian, can be generalized to describe a tetratic order and also higher p-atic orders in the fractional Hall effect. And I showed you that the Lagrangian in spin 2 case can be obtained from the Fils-Pauli Lagrangian after performing a suitable non-relativistic limit, and this holds both at the level of the field equations and at the level of the action. In the spin 4 case, it's possible to generalize this construction without much problem, even though the computations are quite involved. And the result is likely to hold for arbitrary even spins, and even in the case of odd spins, which is what we were discussing before, that it could be that it's not necessary to restrict the deformations to the ones that preserve C2, the C2 symmetry. So some future directions, maybe related to some of the comments here, is to relate maybe effective descriptions of the GMP mode and relativistic gravitational theories. So the relativistic theories I showed you in the talk correspond to linearized theories, but in the same way as the spin 2 case can be associated, the same way the spin 2 case can be associated to a biometric gravity theory. At the relativistic level, it could be possible to relate these theories to some known gravity theories that admit a biometric description, which is the case of pneumatic gravity. or a slide driven gravity. And maybe the one that you mentioned, John, you said that there is another one, another possible relativistic gravity theory that could be related to diametric, the diametric theory of the fractional quantum Hall effect. So also the topological sector, there are high spin theories that are topological. They are given by Chern-Simons actions under, say, 2 copies of the SLN group. So it would be interesting to see if these higher spin relativistic Chern-Simons theories could be related to the ones I showed you before. And in the spin 4 case, also, if there is a possibility to extend the results to the nonlinear case and to find some analog of gravity, but for a rank 4 tensor, which would be a spin 4 version of new massive gravity. And another possibility is to introduce supersymmetry to describe also fermionic collective excitations, which have also been numerically at least observed. And that's it. Thank you.
Questions? I have a question. Maybe I remember it incorrectly, but as far as I remember from textbook, you cannot have an interacting gauge theory for spins higher than 2.
Mm-hmm.
Is that a problem for your description of spin 4 theory?
Yeah, it's true. There are many no-go theorems that forbid this type of
The no-go theorem requires Lorentz invariant if we study non-relativistic.
So in the non-relativistic case, it could
But
be.
it can
No, if you need Lorentz invariant, then
right,
no-go
and
theorem.
then you will make some non-relativistic approximation of your Lorentz invariant theory.
You should begin, like physically, you should begin to have higher spin from the beginning, or you need to ignore the Lorentz invariant somehow. You need to ignore Lorentz invariant in some sense.
Yeah, but it is possible to surpass these no-go theorems by including like an infinite tower of spins or going to the case of a cosmological constant. So it is possible to define this. Also in 2+1 dimensions, the things become easier. In that case, you don't even need to consider a full tower of spins. There are some, like these Chern-Simons theories allow you to describe higher spin fields up to some finite value of the spin, not necessarily the whole tower of spins.
Okay, thank you. So, more questions? If no, then let's thank the speaker again. Now we will have a lecture on software usage.
Oh, right.
So in
Transfer time, right?
2001.
Okay.
In 2001.